All right, so we have looked at the periodic table. We've seen a few trends, and we've revisited the concept of bonding, and we started with covalent bonding, molecular bonding, and we amplified what we already knew from general chemistry with slightly higher level molecular orbital theory. There is more. Now that we know how to do symmetry operations, the next step is to take individual atomic orbitals. If the symmetries align, then to build those into a molecular orbital, and then blend that new molecular orbital with another bigger one, which will let us to put 3, 4, 5 atoms in a molecule and build the same molecular orbital diagram. It's a bit more complex. And we're going to move on. So, how many types of bonding are there? 2, and what would they be? Covalent and ionic. Okay, those are the big 2. It's not all types of bonding though. How many types of bonding total?
Do you count hydrogen bonding?
Counting hydrogen bonding, it's not a real bond, but it's got the word bond in it, so it's a bond. It's in the book. And then the one that nobody ever thinks about. Metallic. Metals bond to each other. Metals bond to each other in a similar way. Some of what we're going to do today in ionic bonding is relevant to what metals do. And I'll point to it when it happens. But we're not going to pursue it. Okay. So let's look at ionic bonding. Ionic bonding happens between metals and non-metals in a situation where the metal has turned itself into a cation by a process known as oxidation, and the non-metal has made itself into an anion by a process called
Reduction.
reduction. Reduction is the gain of electrons. Oxidation is the loss of electrons. Electrons are negative. We lose them, you become positive. All right. Refer back to your now overwhelming understanding of effective nuclear charge. Effective nuclear charge for a cation of a metal versus the effective nuclear charge of the metal itself. Which one is bigger?
The metal itself.
If you were the right answer, I'd go, you're right. The effective nuclear charge for a cation is larger than it was for the atom that generated it, which means the cation is smaller than the atom. And Z effective, so we did Z effective, and we looked at its effect on radius, and we looked at its effect on ionization energy. Those were the big 2. Something that we never pursued, and maybe it will come back around. Again, we do it in general chemistry. The second oxidation energy is always significantly larger than the first. A couple of times I had the opportunity to say it, and I thought, I'll say it in a minute, and then I never said it. second oxidation energy is always, ionization energy is always big. So the first ionization energy takes a metal in the gas phase and pulls an electron away from it. This would be called IE1. And let's say it is, just made up a number, that's 1,000, let's say it's 100 kilojoules. But the metal that I'm looking at is magnesium. So it has to do that twice. So that would be sequentially through two ionization energies, because you can't take them both at the same time. And this one would be significantly larger than the first one, even for something like a magnesium or a calcium that wants to go to 2+. Why is that?
Because the affected charge is strong.
Okay. Why is that?
Because there's less shield.
And this electron is attracted to that positive. This electron is attracted to the nucleus of this atom. But now I'm separating a plus from a minus, and that additional electron makes it harder to do. All right, so I'm going to make some cations, and they are going to be small, and the anion has a smaller effective nuclear charge than the atom that generated it, meaning the electrons in the valence shell are less attracted to the nucleus than they were in the atom, which means they get a little bit bigger. And so in terms of radius, the anion is bigger. So today we're going to see little cations interacting with big anions. And when you've got little things and big things sharing the same neighborhood, this is the one that's going to dominate what the shape is. So the shape of ionic solids is determined by the anion. Okay, I'm going to put a little clause word here, is largely determined. I'm going to pretend that the cation is not playing a role. But the anion clearly is the most important. There is an I in that. You can't see it. That's right. Okay, so let's do a couple of little thought experiments. Now, we're going to make use of numbers. We're not going to do any math, but there are numbers behind this. And we're going to make use of the numbers the best that we can. But it might not be completely possible for us to have a good idea of how big that ion is. And so some of the time, when we do generalizations about, oh, look, this atom is this sodium and that chloride are here together, and this was going to be this much bigger than that one. Sometimes we don't have access to all the ionic radii, and we're going to fall back and use atomic radii as well. And as long as you pick from the same list and you use the correct math to compensate for that, you're probably okay. You can be okay, as long as the math is constructed to allow you to do that. All right, so I have a metal cation and I have a non-metal anion. And right now they're kind of a long way away from each other. They might be so far apart from each other right now that this anion cannot feel the electric field of this cation. When it does, as this X gets closer to that metal, what it does, it's going to get attracted to, right? So from this distance, oh, I've detected the presence of something opposite to me that I'm attracted to. And then these two will get closer and closer and closer together. And as they get closer, the electrostatic attraction between them will increase. What do we measure electrostatic charge in?
I might have a guess. Is it coulombs?
It's coulombs. That's a physics question. Right. We measure charge in coulombs. That coulombic attraction increases, increases, increases. And then X gets to be here. Guess what happens if those nuclei start to get closer to one another now? I start to get these atoms or ions to get closer to one another. The atoms are mostly empty space. The nucleus is 1/10,000th the volume of the atom. Most of it's empty space. But what's in that empty space? Electrons. And what do electrons do to each other? They repel, because electrons are all negative. So there's an attraction. Come over here, don't get too close. And we can plot those two forces. Energy goes this way. When I'm a long, 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 long way away from you, I don't really have anything on this line, but there is an attractive force that kind of grows like that. And then when you get close, there is a repulsive force. And the repulsive force only matters when you're close in. This repulsion is named after Max Born. And is it Emile Coulomb? I don't remember what Coulomb's first name is. I have two forces, and they're not quite equal. The repulsion happens very close. So if I let those two forces average, I get this. I'm plotting energy versus R. And R is the interatomic or ionic this value right here, that is the perfect distance for the ions to be apart from each other. This is called a Born-Meyer diagram. And it plots energy, which you calculate from Avogadro. Do you want to write do you want to see the equation? Okay. I can half do it from memory. If I didn't bring it, we're not doing it. The equation of this line, energy, is Avogadro's number times the Madelung constant. The Madelung constant is intimately related to lattice energy. Remember lattice energy from general chemistry? Lattice energy is it depends which book you read, whether it's going this way or that way. It's the energy released when two ions in the gas phase combine to make a perfect crystal in the solid phase. And the Madelung constant tells me how much any individual ion is attracted to another ion. It's a measure of attraction. So that's the force that you have to rip them apart with. Z is charge. Charge of the cation times charge of the anion times the charge of an electron squared all over 4 pi epsilon R0. Epsilon is the permittivity of free space. What that means is there's a gap between the ions. That gap is made out of our atmosphere. And the permittivity of free space is how easily can a charge skip from one place to another and have an influence when it's just traveling through a gap and there's no real medium. 1 minus, I'm going to rho over R0. And the rho is compressibility. So we know what R0 is. It's right here. This is compressibility. This is the charge of an electron. These are the charges of the ions, because the energy between a 2 plus and 2 minus would not be the same as between a 1 plus and a 1 minus. This is the Madelung constant. And that is Avogadro's constant. 4 is an integer. Pi is pi. This is epsilon is the permittivity. 3 space. Okay? So this measures basically how much charge do I have and how easily can it pass from one place to another. So we're going to see big anions and little cations come together and try to build individual electrostatic attractions and stick to each other. turns out that an ionic solid is not a little plus and a little minus. Because my next little plus would go here. And then my next minus would go here. And then I would have a plus, and then a minus, and then a plus, and then a minus. And I get a repeating structure. But that's only in one dimension. What I would get here, what would go next to a minus would be a plus, and what would go next to a plus would be a minus. And so I can now build it out into 2 dimensions. And then before you know it, I'm thinking, what do you think's in front of that big negative? A little positive. And so we get repeating structures. Ionic bonds build repeating structures, sometimes called infinite structures. So I have, this is now worrying me. I want to describe sodium chloride as a sodium and a chloride. And I managed to get away with that for the most part in general chemistry, right up to the very end where we did ionic solids. Now you're telling me that in just a handful of sodium, because Avogadro's number tells me that that's a gigantic number of ions, I have an infinite number of cations and an infinite number of anions, all in this big 3D repeating structure. Well, I can't possibly write that down. But because it repeats, the repeating pattern is called a motif. And the smallest 3-dimensional representation of the motif is all I need to describe. I don't need to describe 1,000,000 ions in an array. Oh, that's a good word. They are arrayed. My repeating pattern is a motif. And all I need to show you is something called the unit cell. And the unit cell is the smallest representation. In 3D. Of the bonding motif. Okay, let's run through a few. A couple of the really simple ones are not truly ionic. They kind of slip into the chapter though, because, hey, while we're here, we might as well. So something like cubic. Cubic would only be just one type of atom. What we're going to look at is more than one. We're going to start with something really, really simple. Common. BCC is body-centered cubic. All right. Now, there are 2 ways to project a cube. A projection is a 2D representation of a 3D object. There is the, don't bother writing this down, okay? There is the isometric way. You start with a vertical line, and then from that, we're going to splay out at 30 degrees. This angle is 30 degrees. And then at equal distances, we make verticals. And now we join everything at 30. Okay? And anything that's inside the cube gets a dashed line. That's isometric. That's isometric. Both these angles are the same. And this distance, and that distance, and this distance, they're all the same. You set them with the compass, and you draw it out that way. This is not the representation that we use most of the time. The one that we use most of the time is this one. You start with a square, and that square has a horizon and a vertical. And then at 45 degrees, you make a new line. And the trick with this geometry is this perspective, because it's at 45 degrees, is now exactly half the length of here. So this bond going back needs to be this long. That's how we draw a cube most of the time. Okay, in a body-centered cubic, anions are here. I'm going to put the nucleus of the sphere of the anion at every corner. And then I'm going to put my cation at the center of the cube. Okay. A couple of things that we can take away from this diagram. Let me do this first. What we've drawn on the board is the unit cell. It is the smallest repeating description of what's going on inside this enormous three-dimensional array. So here's a cube. Guess what is to the immediate right of this cube?
Another cube.
Another cube. Guess what's above this cube?
Cube.
Another cube. And then to its, and then in front of it. Okay? So these ions that I'm drawing on the corners, if I can go back and find one, that one there, it's shared between this cube on the left and this cube on the right and this cube out in front. Okay? Which leads us to this. Just how much of this ion, top left front, how much of that ion is inside the box?
Is it 1/6?
It is not 1/6. Find the box. Find the box.
Let's see.
Find the balloon.
This is
Here's a box, there's a corner. Here's a spheroid. It's gonna pop. I have a couple of places that you can be. Where we started is, yeah, I know, is here. How much is inside the box? Okay, let's ask some questions, some dumb questions. Is all of the balloon inside the box?
No.
Is half of the balloon inside the box?
No.
Is 1/4 of the balloon inside the box?
No.
Half. So if it were on the face, then half of it would be inside the box and half of it would be on the outside. So what about now? If you split this in half, and then you split it in half again, that would be quarters. Is 1/4 of it inside the box?
No.
No. It's split in half, and then split in half again, and then split in half again. So how much is inside the box? 1/8 is inside the box.
It's so difficult.
Each of those spheres is only inside the box for this part, which is 1/8 of it. 1/8 of it is inside the box. How many anions do I have?
8. Oh, man, that makes sense.
I have a charge for my anions. Anions at the corner, I have 8 of them. Each of them is 1/8 inside the box. Where's my cation?
Inside the box.
It's at the center of the box. There's one of them. How much of it is inside the box?
100%.
+1 plus -1 equals 0. Therefore, this repeating structure does not want to rip itself apart. That is a body-centered cubic. We're going to do a couple of things with body-centered cubics. The example of this would be cesium chloride. couple of other different types of body-centered cubic. What else have I got? The cesium chloride, big one. I think zinc sulfide. Yeah, zinc sulfide also is. Zinc sulfide's different because that's a 2 plus 2 minus. This is a 1 plus 1 minus, which leads us to one other thing that we got to pick out, and it is this. Coordination number, which is C dot N dot, not CN, because that's cyanide. The coordination number tells us the number of objects geometrically arranged around another central object. What's the coordination number for cesium in this cubic-based description?
8.
8. That central cesium sees the 4 anions on the top and the 4 anions on the bottom. It does not see any other cesiums, because the next cesium is in the box over, in the box above, in the box behind, in the box in front, in the box below, or in the box on the left. The cube has 6 faces, 8 corners, 1 center. How many edges does it have? 12. So the coordination number here is that the cesium has a coordination number of 8. And 8 is a cubic number. All right, the other big one that everybody's supposed to know is face-centered cube. Face-centered cube is also something called cubic close packed. We're going to see 2 motifs for close packing. They are cubic and hexagonal, and both of them have hexagons in. Only one of them propagates that hexagon, and the other one doesn't. Okay, so the big member of this geometry is sodium chloride. How much of this did you do in general chemistry?
Would you ask me?
How much of this did you do in general chemistry?
Not specifically.
I do a little bit, not much. Okay. I'm going to put anions at every corner. And anions on every face. So that's top, going to put a cation at the center of the cube. And then I'm going to put a cation on every edge in between the anions. This is face-centered cubic. Here's one that I made earlier. So what we have here are the big colorless spheres. Those represent anions. And the tiny little blue spheres, those are cations. And I have 5 anions on the base, and then 5 on the side, and 5 on this side, and 5 on that. So each anion is on every corner and on the face. And the cations just kind of squeeze in between. We're going to invent a new word, and the word describes these in-between spaces. The in-between spaces are called interstices. And the description, the adjective to describe sitting in an interstice is interstitial. Interstitial means between. These tiny little cations sit between the giant anions. Okay, can we imagine this structure with the little blue balls taken out? It would have no effect at all, right? It's the anions that have decided what this geometry is. The cations play a little role, we're going to get to that soon, but the anions dominate what the geometry is. Okay, let's look at our occupancy. I have anions at the corner. How many anions do I have at each corner? I have 8 of them. And how much of the sphere is inside the box? 1. I also have anions on each face, on the center of each face. How many faces are there in a cube?
6.
So I have 6 of these on the faces. How much are they inside the cube? Do I have any other anions in my unit cell other than the faces and the corners? No. So this gives me a negative charge of 4. Okay. Let's look at the cations. There is a cation at the center of the unit cell. Just the one of them. It's completely inside, and therefore it is 1. 1 times 1 equals 1. And then I have cations on the edges. How many edges do I have?
12.
And how much of each of those cations is inside the cube?
1/4.
And the +4 and the -4 cancel each other out. Okay. What's the coordination of number of sodium in this face-centered cube? And if I know its number, I also know its geometry. In looking at the coordination number of the sodium in this description, am I going to pick one of the sodiums from an edge? No, pick the one in the center. So look at the one in the center. How many, that's a sodium at the center, how many chlorides are surrounding it?
14.
Closest neighbors. Maybe I didn't say that completely correctly. Closest. Remember, this is a repeating infinite structure. If I counted all of the chlorides that are in it, there would be an infinite number of chlorides. What is it closest to?
The bases, yeah.
It's at the center of the cube. So it is immediately above that one. And that distance has to be exactly the same as that distance, top and bottom. What else?
Left and right.
Left and right. To cube, these distances all have to be the same. And then front and back. What's its coordination number?
6.
What's its geometry? A central atom, equidistant to 6 objects.
Octahedral.
That's octahedral. Which we give symbol capital O, lowercase h. So, now that I'm done with my diagram and I can destroy it, I can turn that central sodium into 2, not if I'm this close to it, square-based pyramids. Okay, bam, bam. That's octahedral. 8-sided. 8 triangles put together. So the holes that the anions leave behind can be octahedral. What did we say that the big 3 geometries in inorganic chemistry going to be?
Tetrahedral.
Octahedral,
Tetrahedral.
tetrahedral, square planar. Yeah, there's some trigonal planar in there as well. But square planar is going to be our other big interesting one. Meet the octahedron. The octahedron is the gap can't even see it. There is a little tiny blue ball at the center. There it is. A little blue ball at the center of this thing. And it is equidistant to its 6 nearest neighbors. Okay. So now that we know a little bit about what's going on, we have to go hunting for the other one. And the other one is tetrahedral. The anions are these great big things, and the cations just sit in the gap. And there's going to be 2 places, or 3 places. 3 places where they're going to sit are going to have coordination number 8 cubic. It means it will have 8 neighbors. Octahedral, 6, or the missing one that we haven't seen yet, tetrahedral. And the geometry depends on 2 things. One is something called close packing, which we'll do soon. And 2 is the radius ratio. And I was looking around this morning to see if I could find anybody doing radius ratio the upside down version of the way that it's in our book. Because I kind of remember learning it upside down, a different way than is in our modern book. Radius ratio, everywhere that I looked, was the radius of the cation divided by the radius of the anion, which gives you a number less than 1 because cations are small and anions are big. And I kind of sort of remember doing it the other way, that having a positive number, and the bigger that it got, the more. All right, let's look at this. This can be called gamma, or sometimes it is. This is the radius of the cation divided by the radius of the anion, okay? And obviously, the cation is small and the anion is big, all right? In order to figure this out correctly, we could not rely on data from a table that gave me the atomic radii. These really need to be ionic radii. Okay, this is the quotient of the ionic radii. It says cation, so I think that's fairly obvious. All right, that's going to come out to be a number, gamma. When gamma changes number, a couple of things happen. Not going to do geometry. Just going to say coordination number. We can figure what the geometry is later. Okay. So we've got a sliding scale. If it's really, really small, then your molecules are your structures are unstable. But we've got a couple of things here that we can recognize. From 0.225 to 0.414, that's kind of oddly specific. The coordination number is 4. And that's I'm erasing this, I probably need it in just a second, never mind. That gives me a tetrahedral hole, a tetrahedral interstitial gap. If it's between 0.414 and 0.732, the coordination number is 6, and your geometry for your cation is now octahedral. And if your value is between 0.732 and 1, the coordination number is 8. And your geometry for that central cation is cubic. All right, so here's a couple of things. Every textbook uses the same example, tired old examples, which is good for us because we're only going to see a handful of them. I'm going to start showing you some slightly more complicated ones with multiple ions inside, specifically just to see what's in the gaps. So this is zinc sulfide or zinc blend and copper chloride. We see sodium chloride, we face sense of cubic, as is magnesium oxide. 1 plus 1 minus, 2 plus 2 minus. And then we've already seen cesium chloride to the cubic. Okay, so the cations play a small role. The geometry is definitely dominated by the anions because they're enormous. But a larger cation is going to force more space for itself. And I'm going to slip. As you look down the periodic table, sodium is in period 3, cesium is in period 6. So cesium is significantly larger than sodium. And as it swells, it pushes out its coordination number from 6 to 8. Okay, just demands a little bit more space. But look at how much space it's actually demanding, very little. Okay. All right, now we're going to discuss what this is. This, close packing. Close packing is something that is relevant to metals and is something that you absolutely have to understand in terms of what it is and what it's not. Okay, so on your page, give me 20, a representation, a two-dimensional representation of 20 spheres as close to each other as they can possibly get. Go. Oh, you've got the right paper. So I'm coming to you first.
Oh,
For
God.
those of you watching at home that can't see, Peyton is using reach the paper. She's using this type of Somewhere at home, I still might have it. I actually had hexagonal paper. You can buy it. Why are you talking to me about hexagons? He's given too much. I've said too much. I'm going to shut up now.
Oh shoot, did I do this one?
Give me a two-dimensional representation of a three-dimensional object in which the circles, which represent spheres, are as close to each other as they can possibly get. So, this is a skill. You're building a skill. And that skill is drawing uniform circles.
It's a hexagon. What's that? You want us to draw a two-dimensional representation of what it looks like in 3D?
Doesn't matter. So, okay. So, task number 1, find a pen that works. Task number 2 is to write your circles, which now represent spheres, as evenly as you can. These should all be the same size. And they should almost touch each other. Linus Pauling, he had his hand in absolutely everything. He's the guy that dictated what the spacing between the anions needs to be. This is too far, touching is too close. We write them as a representation actually touching. They need to be touching, back off a little bit. There's actually just a tiny amount of space between them. They're almost touching. All right, there you go, uniform, one-dimensional. My second row, see this? If I did this and drew another set of rows, that's not close packed, because I can do better than that. See how big this gap is? That gap right there. I can forego that if I don't have these spheres touch each other right at the apex. What if I sit in the indentation of the row above it? And then my next row sits in the indentation of that. I'm getting a bit sloppy now.
Yeah.
And then my next row does this, okay? So this is wrong, and this is right. This is as close as you can get. And if you take a box of golf balls, or a golf of baseballs, or a box of basketballs, or volleyballs, and you put them in a box, and you jiggle it about, then they will naturally adopt that representation. This is close packing, where the gaps between them is really, really tiny, and each sphere sits in the indent of the one next to it. Okay? The third dimension gets a little bit tricky, but this is just 2D. Okay? If I pick one of these out and I look at what it's touching this, and this, and this, and this, and this, and this. That's a hexagon. There are hexagons in nature because there are spheres in nature. And a sphere is the most efficient way of encapsulating anything because it gives us the most amount of volume for the least amount of surface area. And when I close pack spheres, I make hexagons. We're almost ready to go. Okay, so time is up. Here's what we do next. See this close pack set of hexagons? My next row goes in, and it sits in the dimple of the spheres below it, and it will form its own hexagon on the next layer up. And then the layer on top of that will sit in the dimples. Only when we get to the second layer, the third layer has a choice. Do I go in the dimples that are immediately above the first layer, or do I do it in an offset position? Because one of them is going to give us octahedron, and the other one's going to give us tetrahedron. And we will deal with that on Thursday. It would not be a bad time for you to read the book, look at YouTube videos. We're going to have things called ABC repeating structures and ABA repeating structures, and it's not easy to draw. Okay.
Do you want the homework?
Oh yeah, homework. Thank you. Let's have it.